Okay, hello. Thank you very much for coming. My name's Adam Warski. I come from nearby, from Warsaw, Poland. So I guess, coming here, you might have like two objections for the talk, or you might be wondering about two things. So first of all, like, who is this guy to tell us what functional programming is, right? Because we are at the function programming conference, like, shouldn't it be obvious for everything, right? And that might be the second objection. And of course, in a way, you might say that it is obvious, right? Functional programming is simply programming with functions, right? And that could really be the end of the talk. But it would be a very short talk, of course, and not very interesting. But actually, when you start wondering what does functional programming, what does programming with functions really mean, I think it stops being obvious. So when people say to you, like, what does it mean when you say that you code in FP style? So what does it mean specifically and practically, right? So I got introduced to functional programming a long time ago. It was my first lecture in my first year of studies, and we were asked to choose either the imperative approach or the functional approach for introduction to programming. I had no idea what either of those meant. I only knew some Pascal and BASIC. But the functional programming track was kind of the more, maybe not elite, but it was like, it had limited capacity, right? So I chose the one with the limited capacity, not the default one. I guess, throughout the year, as we learned functional programming in a very basic form, we kind of got to feel what functional programming is, but without any specific definitions. So I think a lot of people kind of feel that the functional programming is different from imperative, but it's not that immediate that you can actually explain to like a long-time Java programmer, a long-time C# programmer, what the differences are. So that's what I would like to try to capture in this talk. And to answer the question, like, who's that guy that tries to tell you what's functional programming, and quite probably you know better than me what FP actually is. So I've been doing Scala professionally for, what's the date here, 2010, so 15 years. So that's one of my first commits in Scala. I was implementing some kind of method that actually is in the standard library, but I didn't know it back then, so I did my own. So I've been doing quite a lot of Scala, and I've seen Scala evolve over the years, taking different approaches to solving everyday problems. So, Scala is quite often used in an industrial setting, meaning that it's used to write business applications, like everyday applications, web services, things that interact with the database, some like back office, and so on and so on. And there has been a number of different approaches in the Scala community that took functional programming either very far or sometimes stopped midway. So we started with Lift. Maybe some people remember that was like a web framework that used actors and a lot of plain Scala. Then we moved on to Akka, which had a lot of actors, right? Debatably functional, but it used like immutable data structures and so on. It was also based on futures. Then this kind of evolved into more like Haskell-inspired FP with introducing the I/O monad, which was called task in Monix. Then we abstracted over the monad in Katz effect. Then we kind of took a step back and fused all the monads together in Zio, so that we have one big monad that does everything. And now we are kind of going back to direct style, maybe trying to get rid of the monads. So, this might be one more instance of this curve where you actually, a beginner, so you just use Scala, like the native Scala, then you try very hard and squeeze as much FP as you can. That's where you would have all the tagless final, abstract monads, and so on. But then you come to realize where the real value of the various constructs that FP offers really are. And in some ways, I view Scala as a proving ground, right? There has been a lot of potholes of experiments that worked and experiments that didn't work. And we can now gather from this experience. I think Scala is simply a good representative of how we can learn what is valuable in FP and what should we advertise also to other people when we talk about FP, right? Because maybe it's not a belief, but I somehow feel that FP is the better way to do programming than imperative, for example. But it is a claim that you have to somehow prove with some practical statements. So yeah, you know, and FP and Scala is not the only language and approach which has this phase of experimentation where we have discovered what's good and what's bad. Like object-oriented programming went through the same phase, right? We had in Java, we had a phase of representing everything as an object and using inheritance for everything, right? It didn't end well. Like now it's considered an anti-pattern to do too much inheritance. It's said, you know, you should prefer composition over inheritance and so on, right? So object-oriented also had this phase of discovery, and I think we also had this phase of discovery in FP, at least in commercial FP, that we might now learn from. Yeah. So what is the true value of FP and how much FP is enough is something that we'll try to answer. So first of all, I would like to take like a practical take on functional programming. You know it when you see it, right? So we will take a look at some code snippets, and one of them will be, well, at least I will attempt to be more functional, and the other one will be like non-functional, imperative. And we will try to see what's the characteristics of the functional code and of the non-functional code. So they will try to distill the traits of functional programming. So we'll start with a very canonical and maybe obvious example of collection transformations. So on the left, right, it is your left as well, yeah. So on the left-hand side, we have something that you would probably call a functional approach, and on the right-hand side, we have something that you would probably call imperative approach, right? We have a collection of numbers, and we want to do some simple transformation like mapping, filter, and reducing, right? So what is it about this left code snippet that makes it functional and about the right code snippet that makes it imperative? So one thing that's immediately visible is that the left-hand side snippet is written in a much more declarative style, right? It is also arguably easier to understand what the transformation actually is, right? To understand the transformation in the imperative style, you have to do a lot of manual parsing, that there's some duplication, some filtering, and so on. The functional style here is much clearer. But on a more lower level, on a technical side, what we have, of course, is a lot of function applications, right? So maps, filters, reduces, these are all function applications. We have function composition, right? The output of map is the input of filter. The output of filter is the input to reduce. So function composition as well. We also have higher order functions, so functions which take other functions. So these are like some very basic characteristics of functional programming. On the other hand, so the alternative that that imperative programming offers are explicit loops and explicit control flow, right? Because of the declarative nature of the functional approach, this is hidden inside these functions. And the other approach, the alternative, would be to use explicit control flow, so for loops, if statements, and so on, instead. So that's like the very basic characteristics. So let's continue with the collection theme. So here we once again have two code snippets. And they are both kind of functional because they use high order functions. They call the filter method. So what's happening here is we have a menu, and if somebody is vegetarian, we want to filter the menu so that every item only includes non-meat ingredients. And if somebody is not vegetarian, that's maybe a misrepresentation of non-vegetarians, that we require that every meal contains meat. So that's maybe not the best example, but it's an example. Anyway, so on the left-hand side, so the left-hand side would be like the less functional one. The right-hand side would be more functional one. And that's because we, on the right-hand side, we extract the predicate with which we filter the collection to a value, right? So representing and the ability to represent functions as first-class values is also something that's very characteristic of a functional language. And this allows us to avoid code duplication that we have on the left-hand side. Moreover, on the right-hand side snippet, which is like the more functional one, we have if as an expression. In many languages, if is a statement, and having our programming language constructs be expressions is also very characteristic for a functional language. It also is something that helps us really to work with function composition and function application, so something that we have seen in the previous example. So now moving on to like data definition, right? So here we have the same functionality written in two different styles. So we have a mapping from people, from persons to addresses, and we want to update that mapping because when Chris turned 30, he decided to move to Krakow because it's such a nice city. And we have two ways of doing that, right? On the left-hand side, we have immutable data structures and we have immutable maps. So if we want to update the mappings, if we want to change our data structure, we actually have to create new copies of these data structures, right? On the right-hand side, we have like a more traditional Java approach where you have mutable classes where you update the data by calling setters. You can update the mapping in place by setting a new value for the key. The Java approach here, of course, would be the less functional. The immutable approach would be the more functional, and this is also quite characteristic of many functional languages to work with immutable data structures. And this is an example of a more common theme of limiting effects, right? Having mutable data structures and having methods like setAge over here or like map.put. So these methods, they don't have any meaningful return values. They are called only for their side effects, right? So in the functional approach, we actually want to compose functions. We want to apply functions, right? And we can only do that if the functions have meaningful return values, right? So we cannot compose the void result of setAge with anything. So like the Java approach is effectful because it has side effects, and if we try to limit the effects, we immediately get the benefit that we can actually work in a more functional way because now, actually updating Chris with a new age yields a new value which we can manipulate, right? So this automatically allows us to work with functions. And we can take this observation about limiting effects a bit further to limit all side effects, right? So here we have three representations. It might seem to be exactly the same, but when you think about the semantics of what's happening here, it is not. Because the first example, there's like a series of method invocations. Each of them has a side effect, right? These side effects might vary. So, here it's launching a rocket, so something that we do every day at work. When these methods are called in the first snippet, these effects are immediate, right? They immediately happen. On the other hand, in the middle snippet, so that's written in Haskell, we only construct a description of our side effect in computation, right? So what we do is we create a data structure which we can then somehow manipulate. So once again, instead of having some method which doesn't return a meaningful value, we create a method which creates a meaningful value which we can further which we can further manipulate. So here these examples are very similar because there's no like control flow, there's no conditionals, for example. So they would get, so the Haskell version would get considerably more complicated if this conditional logic was introduced, and we'll see examples of that later. In the last snippet, it's kind of a middle ground. So this is written using Unison syntax. So Unison kind of takes, you can take both perspectives on the Unison. You can take the functional perspective because Unison requires the I/O ability to actually be able to write side-effecting code. However, it doesn't impact the syntax in any way, so you can just use normal conditionals, control flow, and so on. But it's still like suspended computation. Or you can take the imperative view, because you just write out statements and they kind of have effects immediately as they are called. Yeah, so this limitation of effects is another difference. Okay, so now let's look at composing bigger programs from smaller programs. So here actually we have two things. First of all, we have, okay, so what's the example? The example is we have some request that's coming in. We need to parse that request. We need to validate that the data is correct. Then we somehow calculate the total of the order. We apply some discounts, and we calculate, we create the invoice basing on the total and the tax, right? And we can do it in two ways. So one way would be like something that you might see in imperative languages. So the parsing and the validation might throw exceptions. So once again, which is once again a side effect. On the other hand, the more functional approach would represent errors as values. And generally, representing concepts as values is something that's very common in functional programming because when we have a value, we can actually feed it to a function. And we can compose the result of something that produces a value with another function. So instead of side effects, representing concepts as values is also something you see in functional programming languages, right? Here we are using, representing errors as a result, so I guess that's OCaml in this case. And to compose the logic, like on the imperative version, you can see that it's a series of steps, right? First, you calculate the total, you apply the discount, you have some mutable data behind the scenes as well, and then you calculate the total, so it's like a bottom-down approach. In the functional one, you kind of have to see from the inside out, because you first calculate the total, then the result of that is passed to the apply discount function, and so on and so on. But it's a series of function invocations, right? So instead of imperative steps, we get function composition. So once again, a characteristic of functional programming. And finally, let's look at defining data, because that's also something that we do very common, right? We can write all the functions we want, but we first have to somehow represent the data to feed into those functions. And we have two ways of doing that. Right, we can go with the object-oriented approach. So it's like a classical example where you have a shape, and there are two implementations. They both have some private state, like the side or the radius of the circle. They have some methods which allow you to calculate the area, which uses the private state. The state is nicely encapsulated. And there's a radically different approach of using an ADT, an algebraic data type, right? So we create an enumeration where all the cases are actually public and all the fields are public. And then we can write methods which operate on such a type, inspect what type it is, use the data of the particular cases to actually implement the logic. And there's like the classical expression problem, because one variant is easy to extend with new cases, the other variant is easy to extend with new methods. So it's hard to say exactly which one is better. I don't think there's like a practical solution to the expression problem, actually. But it's also characteristic that in functional languages, we usually separate data and behavior, while in object-oriented languages, we combine data and behavior, right? And object-oriented languages kind of emphasize that it's good to encapsulate data and having anemic models. So an anemic model would be something closer to an ADT is actually something very bad in object-oriented programming, right? And not so much in functional programming. So there's clearly a difference in approaches. So here the object-oriented and functional approaches actually are quite on the opposite side when it comes to data modeling, but not also, right? In object-oriented, we interact with objects using message passing, and in functional programming, we usually use composing functions, right? I've talked about states, so these are like, even though, we have languages which try to combine both worlds, like F#, like Scala, these approaches often offer different solutions to the same problems. Okay, so we might summarize our practical, the findings from the code examples that we have seen. So there's a number of traits of the functional approach that we have identified. So we have of course, using functions to define the logic of our program, function composition, function application. We are using higher order functions, so functions which take other functions. We can represent functions as first-class values. That's opposed to having code duplication, having loops. We prefer to use expressions in FP instead of statements. We prefer to use immutable data instead of mutable data. We prefer to limit effects and represent effects and represent concepts as values instead of having immediate effects and side-effecting functions. So, this is, I guess, a good intuition into what actually function programming practically means, right? It means using these certain tools to actually create our programs. Okay, so now we have the practical side done. Let's take a look at what theory tells us, right? Because there's also rich theoretical material which we might use. So are these traits that we have defined actually rooted in theory? And I guess the first place where we might go looking for a definition and what functional programming really is of course Wikipedia, still at least. And if we go there, we can read that functional programming is a paradigm where programs are constructed by applying and composing functions. So something that we have actually identified on the first example. However, if we assume that applying and composing functions should be the primary way of actually constructing programs, that has a number of consequences. Right? For example, our programs automatically become more declarative. They become like a tree of expressions because we have the top level function which calls to calculate its arguments, it needs to call other functions, so it becomes kind of a tree of expressions. We also kind of need functions as first-class values to do it ergonomically. So the simple requirement that the function composition application should be the primary objective, the primary tool to structure code, already has a number of consequences which require us to at least have access to these traits that we have identified. However, there is one catch with that definition over here, right? We say that we want to apply and compose functions, but then what is a function, right? And that's actually a non-obvious question. If you click on the link in Wikipedia to a function, you will learn that a function is a callable unit of software with a well-defined interface and behavior, which can be invoked multiple times. And it's an okay definition. I mean, we have all used functions in programming languages, right? But that's not the only definition, of course. There's also the other definition, the more mathematical one, where a function is a mapping between two sets, and for each element in one set, there's exactly one value in the other set, and this mapping is deterministic and effect-free. So these two definitions are kind of quite different, right? One is more like focused on the software, on the computer science side. One is more focused on the mathematical side. And actually, we can assume both definitions of a function, but we get different flavors of FP. So the first flavor is something I would call casual functional programming. It's a term I invented, so probably not something that you might be familiar with. And the other one is something that I will call pure FP, right? The pure FP, because it assumes the mathematical definition of a function. It requires that the functions are effect-free, and so on. And of course, the question is, which one of those is the true FP, which one should we use. I think there is some hint that pure FP might not be actually the ultimate answer, because I don't think there's any mainstream programming language which actually allows us to define pure functions and verify that these functions are pure. So, purity is definitely a noble goal, but I'm not sure it's ever really reached in a practical computer system. So maybe casual FP is actually the way to go. But then you can say, okay, so we assume that the function is a callable unit of software, it's a well-defined interface, and so on and so on. And but then this simply means that functional programming with functions defined in that way, all Java methods are functions, right? The C, when we program in C, we call functions all the time, right? So aren't we all doing functional programming all the time? In a way, you can view it as that, but as we have identified, there's many more to functional programming, there's many more traits and many more tools that when you use that when you do functional programming than just calling functions, right? And indeed, if you have like spaghetti code and you try to refactor it to use small methods, because that's a good practice, like everybody in whatever kind of paradigm they are a fan of, will tell you that it's better to have many small functions than big chunks of code that are hard to read. So if you have some spaghetti code and you refactor it to use many small methods, maybe these methods are side effecting and so on, that's of course a good thing, but it's not functional programming yet, right? There's a lot of other things that you might use, like higher order functions, like ADTs, immutable data structures, and so on, that actually pushes you to the casual functional programming approach. Then you can go all the way and actually try to make your code pure by requiring that all of the functions and all of the methods don't have any side effects. You usually have to do it by pure discipline of coding. You can do that. The question is it worth it, of course. And to motivate somehow that maybe purity isn't the biggest, the most important aspect of functional programming, is once again we have a couple of code snippets. They do exactly the same thing. So the first one is like spaghetti code, right? So what happens here, we have some list of users, and we have a list of IDs, and for each ID we fetch the user information from the database, and then we try to partition those fetched users based on whether they like sci-fi, whether they like Star Wars or not, and this is determined by sending an HTTP request, right? And the first snippet is kind of imperative, uses loops, right? So explicit control flow and so on. And we might try to refactor it into casual FP, so that's the middle snippet, and we immediately get much more clarity, right? In the middle snippet, we use function composition extensively, we use higher order functions, we use functions as first-class values, and this gives us a lot of value, right? The middle snippet is way easier to read and understand what the code is actually doing here. So it's a big leap from the imperative looping version. Now, we might try to refactor it further to actually represent effects as values, because in the middle snippet, like the fetch from database, is side effecting, right? The send request is side effecting, right? You don't see it from the signature, so maybe, of course, that's bad. You could do better, but it's already giving us a lot. So now you might want to modify it to actually make it pure by having fetch from DB, send request, return an IO monad, and so on. But then you have to deal with those two levels, right? You have the outer level of the data structure, which represents computations. You have the inner level of data structures that represent lists. And working with those, it complicates the code. So the code stops being that easy to read. So of course, there's enormous value in purity, like equational reasoning, like fearless refactoring, and so on. But there's also some cost, which is the cognitive cost of actually reading and writing the code, the syntactic overhead, and so on. And this skepticism, you might say, about the value of purity and maybe enthusiasm about the value of all the other things in the FP, I think is kind of also what you can find there's a popular Jane Street video. Jane Street is a company, I think it's the biggest commercial user of OCaml out there. It's a financial company from the States. And they have like quite a popular talk on YouTube. It's quite a short talk, like half an hour. Why functional programming doesn't matter. So that's, of course, like a provocative title because they explain why it does matter for them. And they mention like 3 main things why FP matters for them. So first is correctness. They use ADTs. They are able to make illegal states represent unrepresentable. Dexterity. So thanks to static types, there's no boilerplate. And performance, meaning that it's the translation of OCaml code to machine code is predictable, so they can easily understand how the code will perform. What they don't mention is laziness, and what they don't mention is purity. It's actually quite down the list. So it's occasionally useful, but not crucial. And you know, I'm not going to encourage you to use full immutable code and mutable variables everywhere and so on. But I think it's still a very good approach and a very good practice to avoid having global state, to avoid having shared mutable state in your code. So we shouldn't make life harder for ourselves than it actually is. However, you know, you have to keep in mind that the main complexity of our code is of our programs when it comes like to concurrency and so on is still going to be there, right? Because however we have, so here we have like one thread that's updating something in the database and the other thread that's reading something from the database, right? So whatever way we use to represent this code, if it's like immediate effects, if it's I/O monads, if it's abilities, you know, in the end, this is going to run against the real world, and it is going to be in a kind of race condition anyway, right? So whoever wins. And you have to keep that in mind while coding. So this internal representations of our local code base are only limited, right, to our local code base, right? The world out there is still mutable, and it is like a big shared mutable state that we have to deal with. So let's also take a look at, if we want to understand what FP is, at some other sources. So here's like Stack Overflow. Actually, Stack Overflow has, there's like 2 answers that are interesting. One emphasizes that FP tries to avoid mutating state, so something that we have seen. The other, I'm not sure that's correct because I'm not like a historian, but it mentioned that initially, FP originated from like Lisp. Lisp is full of side effects, but what was important in the Lisp world was that you can have first-class functions, so functions as first-class values. And then, like Haskell came and kind of reformulated this definition a bit to emphasize purity and so on. So maybe, you know, this distinction between what I would call casual FP and pure FP is actually something that was out there in history. And finally, we can take a look at, I guess, the classic paper, Why Functional Programming Matters. So this video is kind of an answer to this paper, or like polemic with this paper. So John is actually somewhere here. So in the paper, I guess it's like, you can consider it like classical definition of what FP is. So if we take a look there, we can see that FP is defined by being is so-called because the fundamental operation is the application of functions to arguments, so something that we have identified. If we read the paper a bit further, we can, like, it becomes apparent that functions are here meant in the mathematical way. And the paper also defines like 2 new kinds of glue using which you can define programs. One of them is laziness, and the other is high-order functions. And finally, we can take a look at Reddit. Reddit also has some good takes here. So I think one answer puts like an emphasis on ergonomics and says that a functional language is one in which it would be hard or impossible to do ordinary easy things if you didn't use functions as first-class objects, right? So an FP language would be somewhere where you have to actually try very hard not to use the functional constructs. And of course, it starts with a statement that, FP is simply, it's a vibe, and maybe it is true, like you have to kind of feel it to really get what FP is and what is not. And finally, Haskell, like the classical, I guess the most used pure FP language out there. If we take a look at how Haskell defines FP, they put a lot of emphasis on avoiding mutable state, of avoiding mutation, and actually having pure computations and avoiding effects. Yeah, so I guess we could summarize what functional programming is. So I would say it's an approach to programming where the primary tools to construct programs is applying and composing functions, but we also have all these other tools that we have at our disposal. So we might use some of them, but we don't have to use all of them, right? So functions as first-class values, expression-oriented, pattern matching, immutable data structures, avoiding shared mutable state, representing effects as values or avoiding effects entirely, and separating data and behavior. So this is like kind of like a spectrum how far you can go with functional programming. And then a functional programming language would be a language which allows us to do functional programming ergonomically, and it has to be witnessed by three components, so by the standard library, by external libraries, and by documentation. So it's not enough that a programming language itself allows you to do FP. It has to kind of to cooperate with you on that, right? If the standard library is not functional, you won't write really functional. It won't really. You won't be able to write functional code. Okay, and finally, let's see how this definition holds when we try to apply it to some of the languages that we use. We will actually start with Java. Java probably isn't, so we will look at a scorecard, we will take a look at all these tools that we have identified and how applicable are those tools to our languages. So Java probably isn't like your first choice when it comes to a functional programming language, and probably rightly so. Right, so, in Java you can define functions as first-class values. They improved the syntax for doing so. However, the standard library is very non-functional, right? The standard library, if you want to do FP in Java, the standard library will fight you back because they use mutable collections. It's not that friendly when it comes to passing functions, to using higher order functions and so on. So even though you can define those functions in a lightweight way, it's quite hard to use them. Right? You don't represent effects as values. You can create immutable data structures, so they have introduced records, for example. But once again, it's rather a niche in Java. The predominant way, the whole ecosystem will use immutable data structures all the way. So the score here, even though you have all those, some of those tools, they are not really used in the wider ecosystem, so the score here is not that high. Then we have Kotlin, which kind of improves a lot of Java weaknesses, especially when it comes to syntax. So the syntax to define functions and to define lambdas is very lightweight. The language is much more expression-oriented. So in Java, we have if statements. In Kotlin, these are expressions. The standard library in Kotlin is very much integrated with Java's, so not a lot of points there because Kotlin still uses Java's collections as the base, for example. We do get some higher scores when it comes to the style we write programs. We use more functions. We often have meaningful return values. Still, Kotlin is very side effecty and that doesn't represent effects as values. Now Scala, so I will consider Scala in two variants. The first variant is like the very functional one. So when you combine Scala with things like Katz effect and Zio. On the language side, you get, of course, almost top scores, right? Lightweight syntax for functions. The function library is functional, so it's based on immutable collections. It uses high-order functions extensively. Almost everything is an expression. We have immutable data structures. We try to avoid shared mutable state, especially when using Katz effect and Zio, and we try to represent effects as values. Of course, these are all based on discipline, right? It's very easy to just call a Java function and escape, break the whole purity of the approach. It is quite high, but it's not like the maximum score. Now we might also consider vanilla Scala, where we just use Scala's standard library and maybe some associate libraries, but without representing effects, all effects as values, without using IO monads or something similar. So here we would get like lower scores on representing effects as values. We might represent errors as either's. That's quite common. But in the vanilla Scala, we wouldn't represent IOs as we wouldn't represent all side effects as IOs. So I guess it's kind of a middle ground, which, as I said in the beginning, I think the Scala community is trying to explore a bit more. Finally, we've got two more contenders. So Haskell scores nearly perfectly here. As far as effects as values, right, there's still an escape hatch that you might take. So even though you are encouraged to represent any effect as a value using the IO monad, you can still escape that system using unsafe perform IO, and you won't be able to tell it from the method's signature. So there is escape hatch, hence 1 point less here. Finally, we have Rust, which I think is interesting because it also wouldn't be obvious as a contender for FP. But if you take a closer look, so you have functions as first-class values there, right? The syntax is very lightweight. It's quite expression-oriented. This standard library maybe not very functional. However, when you write collection transformations and such, you do it like with an FP-like interface, right? So you've got maps, you've got filters, all the things that you know from functional programming. Of course, of course, you don't represent effects as values because that's not like Rust things. However, you do avoid shared mutable state, right? That is, in Rust, by construction, like the whole idea about Rust is to avoid shared mutable state in a different way than we do it in like Scala or Haskell. However, the effect, like the end effect is the same, that locally in your program you cannot really unsafely access shared mutable state. Of course, there's still an escape hatch, so there's unsafe in Rust as well, but it scores quite high. So yeah, so that would be our functionality scorecard. Of course, you are encouraged to disagree with it and put your favorite language in there as well. Okay, so to conclude, I would say that functional programming often has the press, and it's often talked about in terms of purity and in terms of requiring to, having to use the monads and IO monad and so on. And I think there's much more value to FP that can immediately improve many code bases than purity. So I would say that, it's a good question to consider whether you are a casual or a pure FP programmer. So there's a couple of must-haves that a functional programming approach must have, right? It's like the using of a functional composition and application, predominantly having a lightweight syntax for functions as values in your language, having the ability to use higher order functions. There's a number of nice to have, so like immutable data types, ADTs, and pattern matching, and all those tools that are really useful and that bring a lot of value if you try to apply them in a code base. But at some point, functional programming does provide diminishing returns. If you can go purely functional, that's fantastic. But I would argue that most of functional programming's value is in the casual variant. And that when we talk about functional programming, we should not forget about all these other benefits that you get. And admit that a lot of us are doing functional programming very often, also in Java, also in Rust and other languages, and that's completely fine. You don't have to go all the way. Okay, so that's most of it what I had. I just wanted to mention my company, so Software Mill and Virtus Lab. These are like two companies in one group. Thanks to who I'm here. What we do is we are like a software development company. We accelerate product development. We hire a lot of people when in Scala, Java, Rust, TypeScript, and Kotlin, if you would be interested. And that's all I had, so thank you very much.
Thank you.